Welcome to this session on NSX-T advanced architecture. I think in the abstract we had concepts instead of switching and routing because it sounds cool, but that's pretty much the same. So while you're going over the disclaimer slide, I have to tell you that my big issue here today is that I have so much content that I'm trying to shove through just 1 hour presentation. We have lots of stuff to talk about NSX-T. We're actually doing a 3-day boot camp on that. So all this to say that not everything is in there. In order to keep this presentation advanced, I'm going to focus on the core component of NSX-T and the on-prem version. So that's going to be a little bit of the architecture, switching, routing, and some firewall. We have this recorded session now that happened on Monday that will give you an overview of what NSX-T can do, basically all the use cases for NSX-T, and I'll be referring to other presentations that are more specific within this presentation. I mean, I'll refer to the security presentation, to the, we have a routing presentation and so on. We also have an NSX-T for cloud and for Kubernetes sessions that are very interesting. So all this to say that this is not the only presentation on NSX-T. Again, we're going to focus on the core architecture of NSX-T. So let's start immediately. And the first slide that you probably have already seen is a high-level description of the architecture of the product. And typically we start with the lower layer, the data plane. And for us, the data plane is a collection of what we call transport nodes. A transport node is basically a device that is prepared for switching packets with NSX. So as long as it's called transport node, it means that there is some code in there. I've represented this as a vSwitch on the hypervisors, for example. But there is code that is here to switch packets. The different kinds of transport node are hypervisors. So I've represented here an ESXi hypervisor and a KVM hypervisor, that the two ones that are currently supported, and we might add others in the future. We have an NSX Edge, which is a kind of service appliance that we'll see in this presentation. And finally, we have a layer 2 bridge, which is in fact an ESXi hypervisor in disguise. That can bridge between the overlay model and VLAN. This is relatively a corner case, and I'm not going to cover it in this presentation. So all those components are exchanging packets, are doing the networking part, and we're going to leverage in most cases an overlay. I hope you're familiar with the concept, meaning that we're not going to interact directly with the physical infrastructure. The physical infrastructure represented below will not see our IP addresses, our MAC addresses, etc., because we're going to tunnel everything over it. So above the data plane, we have the control plane, which is actually a cluster of 3 VMs for scale out and redundancy. Those are 3 central control plane nodes, as we call them. There is actually a local control planes on the transport node. I've not represented them, but it's actually distributed for performance reasons. The control plane is not in the data path, meaning that should those 3 VM die, traffic should continue being exchanged over the NSX infrastructure. So we don't depend on the CCP cluster for established traffic, I would say. You would have problem moving around virtual machine, creating firewall rules, for example, etc. Above our control plane, we have the management plane, which right now is a single virtual machine called the MP node, the management plane node. The role of this virtual machine is to accept UI input or API calls from the users in order to configure the network. To store this configuration, this is what we call the desired configuration, and then disseminate it inside NSX so that it becomes realized and effective, basically. And finally, but that's not NSX anymore. Above that, you have, well, your CMP or OpenStack, for example. So basically, or maybe directly the user, that's what we'll see in the demos. A higher level entity that will make call to the management plane. So this is a classic slide, and what I've tried in this presentation is to show you a little bit more the role of those different components over an example. So we're going to start with a very simple example. I have a lab with 4 hypervisors. I've represented 2 of them. They're prepared for NSX. We're not going to go through the configuration of NSX. We don't have time for that. The 2 hypervisors are prepared for NSX, meaning that they have NSX bits on them. That's pretty much what you can call the vSwitch, the virtual switch in there. The 2 hypervisors are controlled by different vCenters, by the way. That's a way of illustrating that we're not tied to a particular vCenter in NSX-T. That's something new compared to NSX for vSphere. We're completely independent of vSphere, which is just a compute manager for us, basically. And I have 1 virtual machine on each of those hypervisors, and I've represented what we call the VIF, the virtual interface, that if you want the representation of the VNIC of the virtual machine, that's what matters to us. That's where the user traffic is going to come from. So what I'm going to do is that I'm going to create a logical switch. I didn't introduce this yet, but I hope you're familiar with the concept. This is a virtual L2 domain, a broadcast domain, a virtual Ethernet wire, whatever you can call it, in NSX. So basically, I'm going to create a logical switch that I called here WebLS. Those are supposedly web VMs. And I'm going to attach those 2 virtual machines to the same logical switch and do a ping between them. So the creation, you've just witnessed it from the UI of the MP node. It's a matter of going to the switching tab, entering a name, and that's it. You click OK and enter. I don't remember what it was, but you get a logical switch created in NSX. And then you will go to your compute manager and attach your VM to this newly created logical switch. So here I'm in vCenter 1, I'm selecting my web logical switch, and I'm doing the same on the second vCenter. You'll notice that this logical switch is available in the vCenter UI, and of course I'm going to do a ping, so it works. I mean, this is a recorded demo. There is nothing much interesting here. So just remember that we've seen interaction between 2 virtual machines that are controlled by different vCenters. So that's one of the things that NSX-T can do. So now let's go back to our architecture slide, and I've represented my 2 transport nodes, right? The 2 hypervisors, there are virtual machines on them. I've also represented what we call a TEP. So you're probably familiar with a VTEP in VXLAN. So NSX-T doesn't depend on VXLAN, so we just drop the V, and that's a tunnel endpoint. So that's where we're going to inject in the underlay, in the physical infrastructure, our IP, our tunnel traffic. So right now I've represented a single TEP on each of my hypervisor. We could have several of those actually. And I'm going to replay the demo that we've seen earlier on and showing you the different, the role of the different components. So I have to warn you, arrows fly all over the place in this demo. I don't want you to focus and remember the flow, right? I just want you to remember to see what the different components are doing. That's what matters. If you're drowned still, it doesn't matter. Well, you can catch up later, don't worry. So I'm creating my logical switch on the UI, right? So this is an action that I'm doing on the MP node, and the first thing the MP node is doing, I told you earlier on, it is storing the configuration. So basically it creates this logical switch and stores the knowledge of this logical switch in a database. It then advertises that we have a new logical switch called WebLS to the different hypervisors. So now those 2, HV1, HV2, know that there is a logical switch. And that's important because that allows them to present WebLS as an option in vCenter. So that was our next step, right? We went to vCenter and we attached our, let's say, Web 1 machine to Web LS. So this is a configuration on vCenter 1 here, and this results in a call to the host, the hypervisor, right? And on this hypervisor, we have some NSX code again, and this NSX code is actually going to configure the management plane. So I'm going to mention to the management plane, hey, I have this interface called VIF1, so I'm referring to the VNIC here, and I want to attach it to logical switch Web LS. The role of the manager is always to store this configuration, or desired configuration, where we want to end up is logical switch Web LS, and on it, I have a port. Note that it's not VIF1 that I'm storing, it's LIF1. So LIF1 is a counterpart of the VIF. It's the logical port on the logical switch to which the virtual port of the virtual machine attaches. So it will appear later in the diagram, but just remember that there is a LIF and a VIF. That pretty much is the same. They're attached together, but the LIF is the switching component and the VIF is the virtual machine, the compute component. So once we have this knowledge, we're going to advertise to the control plane, hey, now you need to do something so that this desired configuration becomes effective. And I'm going to push this association to all my CCP nodes. I said CCP nodes are multiple because we want scale out and redundancy. Scale out meaning that you don't want each and every CCP node to do the same thing, otherwise it's not scale out, right? So what we're going to do is that we're going to elect a master for this logical switch. There is a zookeeper running somewhere. And let's say that this is the master for this logical switch. Now the controller is aware of the logical switch. There is a more complex sequence that I've not detailed here, where there is a handshake between the hypervisor where the virtual port is located and this particular controller, and we're registering our LIF. We're creating our LIF, so that's the switching port, and we're attaching it to the VIF. So after this, we have an effective configuration of this VM attached to our logical switch, and the logical switch now is a real object. In the meantime, also, the central control plane has learned about the association between the MAC address, actually also the LIF, but the MAC address of the virtual machine Web 1 and the tunnel endpoint. That will be important for switching decision in the future. So again, you don't need to remember all the different arrows that went all over the place, but I hope it gives you an idea of what the different components are doing. So next, we're going to do the same, but now with a KVM hypervisor. So the KVM hypervisor doesn't have vCenter as a compute manager. So the first steps that we described over there don't exist because we don't have vCenter. If you remember the previous example, the real call that created the attachment to between the VM and the logical switch were done by the host that said to the manager, that made a call to the manager saying, attach this VIF to this logical switch. So this is what we, user of KVM, have to do. So we have to identify the VIF of the virtual machine and ask the manager to connect it to the logical switch. And the way it is going to be done is, first we need to identify this VIF, and this VIF is identified by a UUID that you retrieve from, here I have Versh. I'm going to basically dump the configuration file for this virtual machine, and I'm going to retrieve the UUID of its VIF called VIF3 in this diagram. So I'm going to select that, and I'm going to create now a LIF manually on my Web LS and attach it to this VIF, the VIF with this UUID. So I'm going to my Web UI on the manager, I'm going to the port section, and I'm creating a new port, a new switch port, a new LIF. I call it LIF3 Web, LIF Web 3, I don't remember, right? And I'm specifying the VIF, the VIF UUID, and then the rest of the configuration happens, and now I have connected my KVM to the logical switch. And of course, the ping works. I mean, that's pretty much a given here. I'm going to skip that, by the way. So let's go and see the summary, because that was the easy part. Now we're going to go back to our arrows. So I'm sending this configuration to the management plane, asking the creation for a port on WebLS to attach to VIF3. This is stored in the configuration. This is advertised to the control plane, and then we eventually, now the same step as before, we have this handshake, and basically my VM is attached. And you'll notice that at that stage, my controller knows about the MAC address of all the VMs and their location. So, by the way, I want to stress the difference between the manager and the controller here. The manager knows the configuration of the network. It knows that there are 3 logical ports on this network, LIF1, LIF2, LIF3, and the associated VIF. And the controller knows the association, it knows the dynamic information. Not only it knows that those ports exist, but it knows where. It knows the TEP, the associated TEP information. That's really something very different. The location is more of a control, of a compute object. I mean, it depends where your VM is instantiated. The manager don't really care about that. An additional step that didn't exist in, so that where it becomes a little bit edgy. I mean, there is an additional step for KVM that is specific to KVM, is that the controller is going to actually push the MAC to TEP association it has learned to the hypervisor, to the vSwitch of this hypervisor. And the reason there is a difference between KVM and ESXi is that the KVM vSwitch is OVS based. The OVS has a user space and a kernel space. And we can afford to push this table to the user space. We have lots of memory in the user space. And if we need this table, if we need to create flows for this association, we will pull them from the user space in the vSwitch of the hypervisor. In the case of ESXi, the vSwitch is actually based on a VDS, the typical VMware logical switch, a virtual switch, I should say. And we only have a kernel space, and we don't want to waste kernel memory by pushing all these association. They will be pulled from the controller if we need them. So that's a slight difference between KVM and ESXi at that stage. And I'm going to show you now, the unicast packet walk. You sign up for a packet walk as soon as you came to an advanced session. So here it is. I'm sending a packet, a frame actually, we're just working at L2 at that stage, between Web 3 and Web 1. And I'm assuming I know the destination MAC address, I know the MAC address of Web 1. So it's very simple. I send this frame with destination MAC 1. The switch on the hypervisor is going to do a lookup on this destination MAC. It identifies that it has an association between MAC 1 and TEP 1. And it's going to encapsulate the frame into a tunnel with destination IP TEP1. And this is going to go directly to the remote hypervisor where the frame is decapsulated and delivered to its final destination. Very straightforward. What happens if we didn't know this MAC address? That's what would happen actually if we were ARPing. That's the way this would have worked, actually. First, you would have ARP to get MAC 1. So if you don't know the destination MAC address, we're going to flood. And NSX, just like NSX for vSphere, by the way, at that stage, NSX-T, doesn't make any difference between broadcast traffic, multicast traffic, or unknown unicast traffic. So as soon as you are in this BUM category, your frame is going to be flooded over the NSX network. And this is how it works. This is what is called the unicast mode in NSX for vSphere. That's exactly the same. The way we optimize this is by grouping our TEPs, so the tunnel endpoints, by subnet. So here I have, for example, 3 groups of tunnel endpoints with several hypervisor. The reason why this is clever is that typically the hypervisors below a top-of-rack switch are in the same subnet. We typically put them in the same L2 domain. So that more or less allow us to identify the hypervisor, to group the hypervisor per top-of-rack. And what we're going to do is that, let's say that I have Web 1 that injects some traffic that needs to be flooded. We're going to do a head-end replication for the local hypervisors, and we're going to just send one copy to each remote group of hypervisors. Instead of sending here a copy to each and every hypervisor, I only sent it to one. And then this one chosen hypervisor, will do a local replication in its own subnet. So the benefits of doing that is that we've optimized the bandwidth utilization between the different tiers, between the different top of racks. And that's where bandwidth is supposedly scarce compared to the bandwidth within a rack, which is just local switching. So that's how we do flooding. And I mentioned that the controller knew the MAC to TEP association, right? And it is capable of pushing, or the hypervisor can pull this information if needed. But we can also do data plane learning. So again, the controller is not really in the data path, right? So we can survive without the controllers. So how we do data plane learning, that's the same for everybody who is doing an overlay model, right? The mechanism is pretty simple. You look at the frame you receive, and you identify the source IP, which represents the tunnel that injected the traffic, and the source MAC on the inner frame. And now I know that MAC 1 is most likely, you'll see, on TEP 1, meaning on hypervisor 1. So when I receive this frame, I should safely be able to add a MAC 1 to TEP 1 association in my MAC to TEP table on hypervisor, that's hypervisor 2 here. That's all good, but, and that's one of the reasons why I showed you this model for replication earlier on. What happens if we have this intermediate TEP? I showed you in the previous slide that some hypervisor received their flooded traffic from an intermediate hypervisor. That's what we call, that's not in the slide, that's what we call an MTEP. This engineering term might leak in some documentation. But you have this intermediate guy that has here, that's hypervisor 4, that have received the traffic from TEP 1, and that's going to relay it to TEP 5 here, right? So if we carry on doing this model for this example, the problem is that now the source of my tunnel is TEP 4, and I'm going to learn wrongly that MAC 1 is on TEP 4. This is not appropriate. It's on TEP 1, right, on hypervisor 1. So in order to solve this problem, we need some metadata. Metadata is some information that we can attach to our tunnel, and that is not the data. That is not the encapsulated data, obviously. So here, we're going to attach a tag that identifies the source TEP to the frame that we're flooding. And when we do this intermediate relay on hypervisor 4, the metadata is maintained. So the source IP address has changed, but the metadata is maintained, and thanks to it, I can now learn the right source TEP. The reason I showed you this example, you don't really need to remember that, but it's just to stress that metadata is extremely important in a network. This is something that is being used internally. I'm coming from Cisco. I worked on hardware switches for 17 years. In a distributed physical switch, on the inside of your fabric, if you want, you have this kind of metadata. This is all internal, you don't see it, right? But you want, when you have a distributed switch, when you are about to send your traffic to some destination port on this physical switch, you might want to know where this traffic is coming from, for example, or what access list you need to apply to it, those kind of stuff. This is where metadata are important. And typically, as a hardware guy from my time in Cisco, when you have an overlay encapsulation, you want something that is very fixed, very deterministic, because all this is going to be implemented in hardware. You want all the fields of this encapsulation to be known ahead of time so that I can build my ASICs to do something with this encapsulation. Meaning that if I come up later with a feature that needs some additional bits in this encapsulation, I'm out of luck. Or I'm hijacking some reserved bit or unused bit in the encapsulation, and I hack this around. That's how you end up in some vendor's implementation with some enhanced VXLAN or super VXLAN or whatever name they can give it. So for us, VMware as a software company, that's completely the opposite. We want an encapsulation that is as flexible as possible, where we can add this kind of metadata when we want, when we develop new features, so that we don't rely on the hardware anyway, so we want total flexibility so that we can build quickly new features. And that's why we're going to leverage Geneve for NSX-T. I'm not going to go into the detail of Geneve, but the only thing you need to know is that it's a very basic model. Basically, we've taken VXLAN and we've added the capability of adding type length value fields, some TLVs, where we can add metadata. And we've not defined what those TLV are. That's what is freaking out hardware vendors. We will define some, or even partners working with NSX-T will define their own metadata if they need to, for example. But this is not something that is part of the spec. So it's a very open spec. It doesn't provide much, frankly. So the trick is that nobody should care about the encapsulation that NSX is doing, right? It's a little bit as if my employer wanted to know the color of my pink underwear, right? They don't have to, and if they want to, it's actually a red flag. There is a problem with that. Here it's the same. The tunnels are only used between NSX components. So you should never need to know what is in our tunnel. That's like using the traffic on the backplane of this physical switch, if you want. Note, however, that, we have the capability of looking into those packets, because Geneve is an IETF standard. I mean, you can look at the format. We have Wireshark dissector, stuff like that. I mean, you could look into those, but again, it's not needed. And at last, we NSX are flexible and we can change our encapsulation. Those are point-to-point tunnels we are doing. So if we absolutely need to talk to a hardware device using a tunnel, we could send them VXLAN, for example, a VXLAN encap just for them and keep talking Geneve to our other transport nodes. So it's not really a big deal for us, the kind of encapsulation. We took the most flexible one. I insist so much on this because it is confusing a lot of customers. They're being told by their hardware vendor, oh, that's a new encap, well, how are we going to do that? That's really not of their concern, and that's not a problem for you. Let's go to the routing part. I'm roughly on time. I cannot waste any time here. So I had my 3 web VMs, right? And by the way, I forgot to mention that you saw switching between hypervisors, right? That's an additional nice stuff of NSX-T. I've added another logical switch called app logical switch with just one VM app 1, I think. And I'm going to create a router so that I can route between my 2 logical switches. I created a router that is called a tier 1 router. We'll see later why it's a tier 1 router. And the way you do this is simply by instantiating this router and creating manually. You need to give it IP addresses, of course. So I'm going to give an IP address to each of the links that connect to the respective 2 logical switches. So I'm attaching to WebLS, and then now I'm configuring the connection to AppLS. I'm giving it an IP address, which is going to be the default gateway of this virtual machine, by the way. And once I've done that, I have connectivity, and I'm going to show it to you with not a ping, but this time a trace route. So what is important here is that I've configured, and same for the logical switch. What I think is really cool here is that I've created a router, I've instantiated a router, I attach it to 2 logical switches. It works. My trace route shows you that I'm going through my default gateway, my 2 virtual machines have connectivity at layer 3 between each other, and I didn't change anything on the physical infrastructure. I think that's really an illustration of the benefits of NSX here. You are capable of instantiating a whole complex network with switching, routing, without having to do anything on your physical infrastructure. That's the very important point here. So from a logical standpoint, you have this big router, this virtual router I've created, right? And of course, I don't want this router to be centralized somewhere, because if my web VM and app VM are on different hypervisor, if I have a centralized router, I need to do 2 hops, 1 hop to the central router and then 1 hop to the destination hypervisor. So we've instantiated this virtual router on each and every hypervisor. And that's really an instantiation. That, again, just like we do on a chassis switch in hardware. You basically have a local router on HV1 and on HV2, and you'll notice that they both have the same IP addresses, right? This is something that is not possible in the physical world. Here we can do it because we are an overlay, and the underlay is not seeing that there are duplicate IP addresses. That's the benefit of the underlay, right? So thanks to that, if my 2 VMs are on the same hypervisor, I can route between them without having to get out. And if they're on different hypervisors, there is only 1 hop. Basically, when we send traffic out of our hypervisor, we know exactly the final destination. It doesn't go through an intermediate node. And you'll notice also that the traffic is asymmetric. We do as much routing, as much determination as we can on the source hypervisor. Here we've done the routing on hypervisor 1, and on the return path, the routing would be done on hypervisor 2. So it's kind of asymmetric. Again, we don't care. Asymmetric routing is bad. I mean, if you've been doing switching in the physical world, because it confuses the MAC learning. Here, those are tunnels. There is no MAC learning in the underlay, so there is no problem with that. A very cool feature available in NSX-T is what we call trace flow. So you remember, we know all the virtual machine in our virtual environment. So I can pick 2 virtual machine, actually 2 VIFs, 2 lifts in fact, in this network, and ask NSX to trace the path of the connectivity between those 2 virtual machines. And you see the detail of all the elements that have been traversed going from one virtual machine to the other. And that's very powerful, actually. I mean, that's where a live demo would be better, because if you over one particular component, it will give you, well, the IP addresses. If you go on a logical switch, you can download the MAC address table. If you go on over a router, you can see the routes. I mean, everything is available directly from there. In particular, also, we see the firewall rules that allow this traffic to go through. We'll see that in the firewall section. But we have a very detailed representation of the virtual network and the component that were used to forward our traffic between the 2 devices. That's pretty nice. So not everything can be centralized, unfortunately. And the best example for that is, what if I have a connection to the physical infrastructure? I mean, this happens when your traffic needs to leave your NSX domain and go to the internet, for example. So the port I've represented here on the top of this logical router is a physical port. It needs to exist somewhere. I cannot play the trick of replicating this port on each and every hypervisor with the same IP address, because this is a physical port, this is a physical IP address, and I cannot duplicate it. I mean, let alone that I don't want to waste 1 port on each and every hypervisors just for that. So all this to say that this port has to be physically located somewhere in a well-known location, and that's where we introduce a special appliance for that called the edge node. So the edge node is not a hypervisor in the way that there is no virtual machine on it, but it has the same router instantiated on it, and on the top of that, it is capable of hosting my physical port. And now, if I have east-west traffic, I will use my distributed router on the hypervisors, but if I have south-north traffic, if I need to get out of my network, I will leverage this physical port hosted by my edge node. So there is something that I'm hiding in there that is a little bit more complex. I'm not getting into the detail, but the router that is on HV1 and on the edge node is the same logical router, right? That's the same instantiation. However, the logical router that is on edge 1 has a little something more. It has this physical port. It means that this router on the edge node represented here as a central component that doesn't exist in the distributed version. That's what we call a service router. I'm not going to go into the detail of that, but you have a component that is centralized on this edge and that you don't have on the other distributed router. So if the traffic is coming back in the opposite direction, I'm going to go through my service router, my centralized module, if you want, but I also have the distributed component so I can route directly to my destination. I do, again, as much routing as I can on my ingress device. It's not an hypervisor here on my ingress transport node. So this guy is capable of switching directly to the green app logical switch. So just remember this model. We'll see it a little bit later on again. So a little bit more about the edge node. So I told you earlier on, this is a service appliance. Be aware that it's not a hypervisor. The component I'm representing here are not virtual machines. They're services running in a kernel space. They're very efficient kernel modules, actually. We can run, routers. I've just shown you. We also have, DHCP, for example. We have several services listed here, metadata proxy, and we have a firewall. So those are those kind of services that can run on the edge, and we'll leverage the edge when we have anything that needs centralization, okay? In terms of implementation, we're leveraging DPDK, which is Intel Data Plane Development Toolkit for high performance. The only thing I'm going to tell you is that we're especially in the, I forgot to mention that the edge can be a virtual machine itself or a bare metal, an appliance form factor. So with the appliance form factor, we really have very good performances. I don't have time to go into performances. I'm going to redirect you to Samuel's presentation that will be much more detailed than anything I could do. But we have very good performances with this DPDK edge in its bare metal form factor. So now let's go to two-tier routing. So I mentioned quickly earlier on when we created this logical switch that it was a tier 1 router, and there also exists a tier 0 router. So the difference between the two is that the tier 0 is the one that can connect to the physical infrastructure. Typically, this is a router that you configure once. And this is a manual configuration because you're tied to the physical infrastructure. You'll have to configure physical IP addresses that go to the physical network. You'll have to most likely configure routing protocol adjacency, stuff like that. So this is pretty much a logical switch that is equivalent to a virtual version of a physical router, right? And that's the only one that can actually host a physical port as I represented earlier on. That's a tier 0 router. And we have the tier 1 router, which is an entirely virtual router in the way that this guy cannot have a physical port, and it can only connect to logical switches or a tier 0 router, right? So this is how it's represented. Typically, that's the one that is instantiated dynamically by your CMP, for example, if you're doing OpenStack. If I need a router, I instantiate it, and I have no dependency to the physical infrastructure. That's why in my example, I chose a tier 1 router, because I could just enter tenant 1 logical router, or I don't remember what name I used, click enter, and that's it. I had created my virtual router. So that's the main difference between those two routers. There is no dynamic protocol running between those routers. That's a very important point. In NSX for vSphere, we had, in order to advertise our routes, we were leveraging the configuration of a routing protocol. Here, NSX is taking care of advertising all the necessary routes. So the forwarding table in those routers are handled directly by NSX. You don't have to configure anything. That's a great thing, in my opinion. So something that is not, that most people don't really see, is that those two kinds of router are still entirely distributed. So here, don't assume that the tier 0 is centralized and the tier 1 are distributed. We still have a distributed version of those routers. So if I have those two-tier routing necessary between two virtual machines, it can be achieved within a single within a single hypervisor. So here, my two-tier routing is done on hypervisor 1 because my two VMs are on hypervisor 1. The traffic doesn't have to get out. And the same if we had to route between two hypervisors, we only have one hop. We do all our routing again on the ingress hypervisor, and we determine the final destination, and we send directly at layer 2 this traffic to the final destination. So that's very powerful, and this is also asymmetric. You'll see that we're not using the same logical switch one way or the other. Now, let's talk a little bit more about what the tier 0 router can do to connect to the outside world. So, from the outside world, a tier 0 router looks like a single box, a single logical router. If you configure BGP, so we can do BGP to the outside world, the physical router will only peer to one router. They think it's a single router, even if it can be actually a collection of different edge nodes. I mean, there are several possible ways of implementing this, right? You could have several interfaces on one edge node, but here I took the extreme case of having 4 edge nodes. That looks like a single BGP neighbor for my external router. We can do lots of fancy stuff on the BGP front, and we can use ECMP, we can filter AS path. I mean, I'm not going to go into the detail. I'll refer you to a routing session that happened this afternoon for more detail on our BGP capability. Some important point that was an important request for NSX for vSphere, we have BFD toward physical to protect our adjacencies, so we can convert quickly. Should a link fail between physical and logical, we can detect the failure thanks to BFD. We can detect the failure quickly and fail over quickly. We can also do ECMP, meaning that we can load balance our routed traffic in both directions here. We can also use, I forgot to mention, static routes if you wanted to. So let me show you an example of ECMP, by the way, and on the left in this diagram, you will see the logical version of it, basically what it looks like from a logical standpoint, and on the right, you will see how the traffic is actually forwarded in the physical network. I mean, physical, meaning our transport nodes, actually. So when I'm sending traffic to the outside world, I'm doing as much routing as I can on my source hypervisor 1, and I'm going to route from tier 1 to tier 0. The tier 0 determines that this traffic has to go out to the, let's say, to the internet, to a physical uplink. So as we saw earlier on, it's going to use this little intra tier 0 router tunnel to reach the service router, the centralized part of this tier 0 router, and then we can route to the outside world. The tier 0 router that is distributed is the one actually doing ECMP, meaning that based on some hash, it can select the other centralized tier 0 router to go to the outside world. And in the other direction, well, that's pretty straightforward because the ECMP is actually driven by the physical router, and it selects one of the two peers that provides equal cost path to the destination. So just looking a little bit inside our network. So this is my final demo on routing, and I'm going to show you how we configure a BGP adjacency to the physical world and how routes are being advertised to the physical world. So on the right side, you have my physical lab, which is actually nested. It's virtual, but let's assume it's physical. I have a single edge node on which I have my tier 0 router with a physical uplink. I have a physical router which is actually a Quagga box, a virtual form factor, but it doesn't really matter. At the bottom, I still have my tier 1 router. You remember the one that we used to route between web and app tiers. It's still there. I mean, it's not connected to the tier 0 right now. There is absolutely no connectivity at that stage between tier 1 and tier 0. So first, I'm going to go to the tier 0, and I already have the plumbing. I already have the uplink connected to the physical router. I'm going to configure a BGP adjacency. And the way I do that is, of course, I'm going to the tier 0 router, and I'm selecting routing, and I'm going to enable BGP. I'm going to give a local AS number. and I'm going to add a neighbor, and it's just as simple as entering the IP address of the neighbor. And it's remote AS, by the way. So this is 200 here, this is eBGP. Now I'm going to configure the route redistribution between my virtual network and my external network. At that stage, I have created a BGP adjacency, but I'm not advertising anything. So I'm going to go into route redistribution, and I'm going to select redistribute NSX static. So I told you earlier on, the routes that are within NSX are entirely controlled by NSX itself. You don't need an internal routing protocol. So those routes, we call them NSX static. I mean, you can like or not the term, but it's called NSX static because it's not coming from an internal routing protocol. So here I have selected, I've created a rule that says advertise all the routes that are NSX static. This is a very flexible mechanism. I could select subnets, there are tons of ways, but here I'm just violently advertising everything. And I'm going to check on my physical infrastructure. I'm going to go to my Quagga router, and I'm going to check what's happening. Oh, sorry. First, I'm going to connect, I forgot this step. I'm going to connect my tier 1, that's a very important one. I'm going to connect my tier 1 router to my tier 0. Right now, before, the tier 1 was disconnected from tier 0, if you remember. Now, I just need to go to my tier 1 router and select attach to tier 0, and I'm selecting the tier 0 I want to attach to. There could be several tier 0. Click OK, and it's going to automatically create for you a point-to-point link between my logical tier 1 router and my logical tier 0 router. And actually, so I've highlighted the link on the tier 0 side. This is called a linked port. So you have link port tenant 1 router. It also gets automatically, magically, an IP address in the 100.64 range. There is an RFC for that, I didn't know. And the IP addressing is done automatically for you. You don't have to do anything, right? And again, those routes are handled by NSX. That's very straightforward. So I just decided to attach my tier 1 router to tier 0 so that it can communicate to the outside world. That's optional, of course. And now I'm going to go to my Quagga router and check if I see some routes on the outside world. And actually, you don't see any BGP route yet. And that's the reason. The reason for that is because the tenant router has not decided to advertise anything yet at that stage. Right now, we're advertising from the tier 0 to the outside world, but we've not chosen, and it is under our control, the owner of tier 1 router, we've not chosen to advertise anything yet. So I'm going to do just that. I'm going to go to the tier 1 router and select the route redistribution. I'm going to advertise my connected routes. And as soon as I do that, if I go to my Quagga router, I now see my routes being advertised by BGP. So that's very powerful when you think of it. That's the example I think that Dimitri is using when showing OpenStack, if you've seen one of his demos. I mean, if you instantiate a new tenant, you can assign it. You can assign IP addresses and have this tenant generate BGP advertisements without ever configuring BGP. This is something that is done entirely for you by NSX. This guy is now, the tier 1 router is capable to talk to the physical world just by mere NSX-T configuration. Okay, we still have time, hopefully. I think I'm roughly on time. I'm sorry, I look like I'm rushing, but we're going to finish with the firewall. I'll be out there for questions as long as you want, okay? I just want to let you know that. So, with NSX-T, we have two kinds of firewall. We have our distributed firewall, which is the firewall that is instantiated on each and every VNIC of a virtual machine. And we have actually centralized is not the right word. We have what we call an edge firewall, which is the firewall that you can see on the top of this tier 1 router here. So that's a firewall that runs on a router. Those are two different kinds of firewall. So distributed firewall is a very important feature for NSX that allows you to make very granular filtering within your data center, because now you can really identify traffic that's a stateful firewall that can be applied even for traffic within the same logical switch. So it's very important. And what I'm going to do to show you is a typical use case where we prevent virtual machine within the same logical switch to talk to each other. That's just an example, right? I'm going to create what we call an NS group. That's just a logical construct that groups objects in NSX-T. And I'm going to create an NX group that group virtual machine with a name that include web in them. So anything that is called web something will be part of this group. I named the group web VMs, of course. And this is a result of my configuration. I have web 1, web 2, web 3. I could have created this group in tons of different ways. I could have used, well, the IP addresses. I could have used a subnet. I could have used a logical switch. I can put tags on objects. This is very powerful. I can put tag on objects and create groups based on this tag. That's very powerful because you can create a tag for a particular function, for example, in your network. Put all your firewall rule to this tag, and then when you want to assign a particular VM to this group, just give it the tag, and immediately it inherits all the rules that have been associated to this tag. Tags can be nested to make complex rules. I mean, this is a very, very efficient mechanism to create firewall rules in NSX-T. So here I did something very basic. I just grouped my VMs by name. And I'm going to show you a trace flow between web VM1 and web VM3, or 3 to 1, I don't remember what I did, just to show you how, I actually skipped, sorry. So I went too far. That's this one. That's the problem with animation, is that this one. I'm going between web VM1 and web VM3. And just showing you the path between the two. They're on the same logical switch, so we just do L2 switching here. But you see that they're going through the respective distributed firewall on the NIC of web 1 and a web 3. That's what is important. You see that they go from one hypervisor to the other, and they hit the firewall on each of the VNIC of those different virtual machines. So now, fast forward, I'm going to skip my group that is being created, and I'm going to create a rule. So this is a firewall configuration in NSX-T. I'm going to create a rule that prevents, oh man, I'm going again. I'm really sorry. This is, once you've lost track, you're, yeah, so this is good. So I cannot get it to work, I'm sorry. And I don't have time to play with this. Basically, I'm telling you ahead of time, I'm going to create a group that prevents web VM traffic originated by web VM to go to another web VM. Here it is working. So this is a list of all the rules that are applied by the firewall in NSX. And I'm going to create a rule. So I'm going to put a cryptic name that nobody remembers after 1 year. That's the way it works for security. And I'm going to identify traffic that is sourced by web VM. So that's my NS group. Anything that comes from this web VM. And destination is another web VM. And I'm going to drop this traffic, right? So that's something that prevents web VM to talk to each other. By the way, this is an interface for all that is firewall related in NSX. It's all a single pane of configuration. It's very nice. So once I have applied this rule, I'm going to redo my trace flow. And you will see, I'm trying to, I don't know where I'm retracing. And you will see that the traffic is not going through. And what is very nice is that trace flow tells me exactly where the traffic has been dropped. You see that the traffic has been sent on transport node 1. It hit the firewall for web VM1 and it gets dropped there. The traffic is not even injected in the network. It is stopped right at the VM level. And the firewall rule tells you exactly, the trace flow tells you exactly which rule. I forgot to mention, the rule was numbered 1025. and you see exactly the rule that led to this traffic being dropped. So if you have connectivity issues in NSX, just go to trace flow, and if you have a misconfiguration in terms of firewall, you will see it immediately from this configuration. This is what happens, if you didn't forget this diagram, when you configure this rule on NSX. Basically, I'm configuring on my manager drop web-to-web traffic. This configuration is stored in my database, and it's pushed to the controllers. Then the controller are going to explode this rule into dynamic objects. It's going to, I don't have the animation, too bad. So basically what it's going to do is that it's going to explode this rule into IP to IP rules. And this is something I'm going to do that is very bad. You see it here. It means that I probably have something that is deselected. Forget about the animation. This is what you should have seen here, right? Basically, this rule has been expanded into several IP-based rules. This is what the controller does. And then it is applied to each and every transport node. Yes, okay. I'm going to zap through. So this is something, so the rule is pushed, and every transport node has actually a granular IP to IP rule that is programmed into it. It doesn't have the high level. The high level is stored by the manager. It's my last slide almost. That's the edge firewall. You remember the one that is applied on the uplink of a router. So the firewall is naturally centralized because we want to maintain some context for the traffic. So we want to see traffic both ways. So we need to put the firewall in a location that sees the traffic both ways. For the distributed firewall, the natural place of centralizing this firewall is the VNIC. So paradoxically, the distributed firewall is centralized. It's just centralized on the VNIC. So the VNIC of VMA sees the traffic both directions. If I put my firewall here, I can maintain my context, the status of all my connections. This is centralized. For my router, things are different. This router is entirely distributed. If you remember correctly, this uplink is actually instantiated on each and every hypervisor. So it cannot be put on one particular hypervisor. We need to centralize it in one appliance, and this appliance is, as for the physical port earlier on, it's an edge node. So the edge node here is going to run this uplink, this what we call this edge firewall as a result, for the gray router here, and my traffic will be steered toward this edge node when it needs to go through the firewall. So you see, I have my traffic exiting my tier 1 router. I put a firewall on the uplink of this tier 1 router. It means that this tier 1 router has a centralized component on an edge node, again an SR, that has this firewall, and my traffic has to do some hairpinning towards this edge in order to have my firewall rule applied, and those firewall rules need a context, so they need to be centralized. So this is another example of traffic flow when traffic is on different hypervisors. So that's it for my firewall section, and you will get more on security with our recorded session from our CTO, Bruce Davey. Wrapping up, I'm just on time. I'm sorry for the mess up about the animation. I worked hard on this. I don't know how it happened. Anyway, basically what you can take of this session is that, well, NSX-T can run across different vCenters. It's not bound to a particular hypervisor type. It is leveraging those edge nodes, which are high performance devices for anything that needs to be centralized, whether it is routing to the outside world of services. And also that all the routing components are handled automatically by NSX. You don't have to do anything manually in your network to stitch those components together. It's pretty neat. And what I would really recommend is that you play with this. And that's why I listed some hands-on lab where you can play with NSX and really see, because I really went quickly over those in order to put as much content as I could on this session. But it's more fun when you play with it, so I encouraged you to do so. That's it. Thank you very much.